Hello everyone, my name is Pei Guo. I'm very happy to present our work on semantic network interpretation to this EIA workshop. This is a joint work with my PhD advisor, Farrell from Brigham University. First, we'd like to provide some background on network interpretation and understanding. Nowadays, people treat neural networks as black boxes. When something goes wrong, nobody knows why. You just stir the pot of linear algebra until it works again. Sometimes deep learning is also called modern alchemy. How can we tackle network interpretation and understanding? And more importantly, how do we define them? Perhaps we can draw some inspiration from planetary science. Tycho Brahe is famous for his observation of astronomy motions. Johannes Kepler makes use of Tycho's observation and came up with his 3 laws of planetary motion. In some sense, interpretation is similar to Tycho Brahe's astronomy observation, and understanding is similar to Johannes Kepler's laws. There are many definitions of network interpretation and understanding, and our definition is as follows. Network interpretation is to know what features a network has learned. Network understanding, on the other hand, is to know why such features can be learned, or how to learn good features. Network understanding is to provide theoretical models, explain the observation, and make predictions about the unknown. We argue that a good network interpretation algorithm should enable us to know how to learn good features and how to learn good network architectures. There are many previous works on network interpretation, and many of them are realization-based. One can interpret a network by directly realizing its filters, but this only works for first-layer filters. Because higher-layer filters works on the composition of lower-layer filters, and directly realizing them doesn't make sense. One can instead realizing the feature maps, maximally activate images, and optimized inputs. One stream of research is called attribution. Basically, it tries to visualize the most important region behind a network decision. Class activation map, or CAM, GrabCAM, and other follow-up papers are examples in this research domain. There are many problems with realization-based interpretation. In one research, the authors find if you replace the learned weights of a layer with random weights, the realization actually looks very similar. In this example, we show 2 visualizations of the same image, but for different predicted category. We see that the visualization, the highlighted region, looks almost the same. To summarize, realization-based interpretation doesn't provide semantic information that are easily understood by humans. Network dissection provides a good example of semantic interpretation. However, in network dissection, a neuron is represented by only one concept. What we'll show later is that there is multimodality in filter representation, meaning that a filter can represent several concepts, and a concept can be represented by several filters. This is also called distributed representation in neural networks. Next, we'll introduce our paper on semantic network interpretation that addresses the aforementioned limitations. In our work, we provide 2 levels of network interpretation. One is filter level, one is decision level. For filter level interpretation, we represent a filter with attribute distribution. For example, in this case, a filter activates. We can say that it activates because of the network found it has long orange bill, or it has long white neck, or long neck, or black crown. Decision level network interpretation integrates filter level interpretation and forms class attribute distribution. In this example, when the network makes its decision, we find that the most probable reason is because it finds black crown, or black head, or red breast, or white breast inside this image. In order to find the attribute distribution, we propose a Bayesian inference framework. The probability that an attribute T can represent a filter F is proportional to its prior distribution, prior probability, and the likelihood that images with attribute T can activate filter F. Here are some textual summarization examples generated by our algorithm. For example, our algorithm looks at image A and says, this is an American pipit because it has short beak, yellow and white breast, brown crown, and yellow throat. Textual summarization also enables network debugging. When a network makes a mistake, we can look at the textual summarization and find out the reason. Sometimes it's because the network fails to recognize the most important feature for a certain class. Sometimes it's because some filters are misfired because of the noisy inputs. Our network interpretation algorithm also helps with network understanding. We're especially interested in the relationship between a network's performance with its distributed representation. We measure distributed representation via two metrics. One is filter selectivity. One is concept sparseness. A filter selectivity refers to its representing a few numbers of concepts. A strongly selective filter only activates on narrow sets of visual attributes. Concept sparseness refers to the fact that a concept is represented by several filters. A sparser concept is encoded by fewer filters. Our takeaway message is that we show a filter's importance is surprisingly negatively related to selectivity. We hypothesize that an important filter may encode some rare concepts, and a less important filter may encode concepts that are already encoded by many other filters. For concept sparseness, generally speaking, better models encode more concepts, and the concepts become increasingly distributed during training. That's it for today's presentation. Thank you.